So this is quiz B for the second half of Unit 3, the last of the new things we're learning in trigonometry, Math 13-16. So we started with polar coordinates in Unit 7.1 for the second half of Unit 3. Give 4 other versions of the given polar coordinates. So these are already an r and a theta. We want 2 other coordinates with r that is positive. Well, since the r is what it is, that means we're going to have 2 other coordinates with positive 5r. It's not going to change. This point lies on the circle that has a radius of 5 at that particular angle. Like, we want it to land in exactly the same spot. 5, 3 pi over 2 is right here, where this distance is 5. Away from the origin in that direction of that particular angle. Now, so if we wanted to get 2 more with positive r values, one way to do it would be to change which direction we went and get a negative theta. So instead of 3 pi over 2, I might be at negative pi over 2. So that's one option. And then perhaps I could go around again, negative, what is that? Negative 1, 2, 3, 4, 5 pi over 2. I just have to count sometimes. Now, alternatively, again, we could have gone around the circle twice this way, or 1 3/4 times there. So that would be then 4 pi over 2, 5, 6, 7 pi over 2. So another option with a positive 5 would be 7 pi over 2. And that would be a positive angle. Okay, but it also wants r to be less than 0. So negative 5 radius. What do we do about that? How do we find an angle if we're talking about a negative 5 radius? So I'm going to draw my point again. I want to be here, but I have to have backed up to get there. So which direction was I facing when I then went backwards 5? I would be facing pi over 2, so that I turn almost like bearings to 5 over 2, or pi over 2, and then I back up 5, yeah, negative radius, negative 5 pi over 2. So that's one option. And then to get another one with a negative 5, I could just go around the whole circle again and call it 1, 2, 3, 4, 5 pi over 2. Or I could go around backwards and have negative 3 pi over 2. Notice that when I changed my 5 to a negative, this particular angle also changed to a negative. I think that might always work, actually. If you go the other way and you back up, you can get to the same spot. So recommend drawing it and then coming up with new ways to get to that same point. Again, every single one of these polar points lands in this spot. This is the standard version that has a positive r and a theta between 0 and 2 pi. So this is sort of our fully simplified polar point. But all these other polar points land in the same place. Convert the polar equation. Okay, so now we're going to need those equations. Those key equations are, x squared plus y squared equals r squared. Tan of theta equals y over x, the rise over the run, the slope. X equals r cosine theta, and y equals r sine theta. Now these two are specifically for turning polar to rectangular. These ones are much more useful for rectangular to polar. So last time in the quiz A, I used these to go from rectangular to polar. I replaced x squared plus y squared with r squared in quiz A. But here I have a polar and I'm trying to go towards rectangular. So I'm more likely to use these. Now the trouble is I don't have I don't have an r sine theta, I have an a sine theta. And a is just sort of like a general placeholder for a constant. If you look in the polar graphs note sheet that I handed out, which I actually do plan to give you on the test, by the way, then you'll see that this has a particular shape and it's already sort of told to you like that, but you need to be able to show me how you know. So the trick for this one is to introduce the missing r. So I have an a, but I want an r, because an r sine theta becomes r sine theta a y. So then we have a times y. But if I multiply this side by r to make that happen, I have to multiply this side by r, which fantastically, so this does turn out to be helpful to have written all 4 of my equations, because this one helps me see that my r squared can become x squared plus y squared. And now my whole thing is already in x's and y's. I've gotten rid of the r's and thetas, and I've replaced them with valid substitutions, like identities, with x's and y's. It's almost like saying, I want to reduce the power, right? I don't want a cosine to the 4th, so write it in terms of something raised to the 1st power, right? So you use a bunch of substitutions. I'm substituting with these 4 equations. Now, this isn't fully complete, but again, this is something I'm going to talk about on Tuesday. I could, or I should, and your homework requires you to group all of these together. I subtracted the AY and I wrote it in a way that leaves me some space to do something called completing the square. I know that you remember this. So if I add something to the left, I have to also add something to the right. Or I could have subtracted it from the left, but I like it on the right for this use. So I'm going to complete this square. Let's see. Right now, my square has a y squared and a negative ay, but I need it to be written as y plus or minus something times itself. This needs to be a square, so I need symmetry. This will be y as well. My y squared is already symmetric. I need that negative a to be split. I want negative a over 2y here and negative a over 2, that's an a, y here. So this is minus a over 2, this is minus a over 2, and this whole thing can be rewritten as x squared plus y minus a over 2 squared once I complete it. So the difficulty is I don't actually have everything I need to force this to become that. I need to add whatever fits into this square, whatever completes it. So a over 2, negative a over 2 times negative a over 2 is positive a squared over 4. So I need to add an a squared over 4 to both sides to complete this square and write it in transformation form. You might notice that this looks a lot like x minus h squared, right? Although it is the y, it's inside that parent operation, so we're gonna treat it like x minus h squared, where this actually shifts it to the right by a over 2. Not right, it's y. It'll shift it up by a over 2 instead of the down that I want it to. So I see y minus and I think go down, but I have to go opposite because it's inside the parentheses. So this graph actually is a circle with a radius of the square root of a squared over 4, which is a over 2, half of my, which is the same as my displacement, by the way. So if I rewrite this, this is a over 2 squared, which means r is a over 2, the radius of the circle that this equation represents. But it's been shifted up by exactly 1 radius, so the center here is at a over 2, and the circle is tangent to the x-axis at the origin, because it's been shifted up by the same amount that is its radius. So if you look at the polar graph cheat sheet, you'll see that it is a circle shifted up by a over 2 when a is positive. If a was negative, it would push it down by that amount, because this would then be y plus something if a was negative. So, cool. Describe the symmetries. Okay, because it's been shifted, the symmetries of this one with respect to the pole, if I turn this whole thing upside down, the pole is the new origin, would it look the same? No. No symmetry with respect to the pole because it has been shifted only in one direction. It doesn't look the same upside down. The polar axis, that's this one, well, no, because if I flip it across that axis, it doesn't look the same. No. But the line theta equals pi over 2 is this one. This is the symmetry that this function has, because if I fold it on across that line, I land back on myself one way or the other. So that is in fact a line of symmetry, the line theta equals pi over 2. So those are the symmetries. That's how to finish the problem. Everything in black would be totally acceptable for this test, although you have to then make the analysis, but you can get this graph from the cheat sheet. We will in fact be doing a ton of this next semester, this completing the square, so it's not a bad idea to learn. But if you don't have time right now, just put it off till next semester. Okay, do your homework. Find the exact modulus of each complex number. All right. The modulus is just the length. It's the radius. Fancy word, right? We decided there was an M, and an R. So modulus. What was the other M? R is radius. Oh, magnitude. Yeah, I think Samira was the one that came up with the idea of modulus, magnitude, radius, MMR, like the vaccine. All of those are the same thing, just in different contexts. So finding this modulus is to take the square root of 10 squared plus 11 squared, which is the square root of 100 plus 121. Now there are still a couple of you I've seen in your scratch notebook that immediately took the square root of 10 squared and the square root of 11 squared, and you're like, it's 21. It can't possibly be 21. It can't possibly be 21. Because if I plot this point, I go over 10 and up 11, there is no way that this length is the same as the sum of those two lengths. Do not square root this until you have done all the addition and multiplication inside. This is now the square root of 221, which is not a particularly interesting number. It's kind of boring. Not even sure what it divides by. I think it might be like 13 times 17 or something, but I don't think it simplifies. How about this one then? So that's the answer, by the way, to be clear. This one would be the square root of 11 squared minus, or plus, sorry, I'm tricked by the negative there, plus the square root of 27 squared. Now I don't bother writing the negative because I know that both of these pieces, once they're squared, go positive no matter what. So I just ignore the signs inside. And this is the square root of 121 plus who knows what the square root of that is, and then I would simplify. I'm not going to do that. Too many numbers, I would screw it up. But the modulus is unaffected by whether you went up or down for your for either component, honestly. It just cares about those side lengths of the triangle. It is the radius, it is positive. Write the component form of a vector v with the initial point. Ooh, so now I've got to think about where I am. The initial point is 2.8, negative 2.1. So this is P. And the terminal point is 9.4, 2.3. So like here, this is Q. Okay? So the vector starts here and goes there. I would love to be able to drag it to the origin and see what it is in standard form, but since I don't have that power, I can define this here distance. The horizontal component of it is going to be the difference between their x components. So this is xq minus xp, because distance is difference. Along a line, distance is difference. And so the x component will be 9.4 minus 2.8. And I do know that it wants to be positive because I've drawn it and I know that I'm pointing to the right. So I've done this subtraction in the right order. Now the vertical component is going to be the difference in the y's. So yq minus yp. So yq is 2.3 minus a negative 2.1. Now this is important to note that I'm subtracting a negative integer, so it should be longer than either one of those because I should be adding those distances, which is great. That's what's happening when we do the math carefully. So the actual final answer is 9876.6 and 24.4. So if I were to drag this vector up here, this point would be 6.6, 4.4. That's the whole idea about standard form. Once I put it in standard form to push it to the origin, my ending location is the name of the vector largely. But when I'm outside of standard position, I do have to do a little bit of math to figure out those components. Find the angle theta between these two things. All right, this is an application of the dot product. So the angle between is the whole cosine of theta part of our definition of dot product. So the dot product was the magnitude of one times the magnitude of the other times the cosine of theta, or it was v dot w, the rectangular way. So the rectangular way of doing that was to take 4 times negative 12, the x components times each other, and add to that the y components times each other. Negative 3, ignoring the j because I just need the component magnitudes. Negative 5. The j just tells me those are the parts that go up. The I tells me they're the parts that go over horizontally. So now this value is negative 48 and this value is positive 15. And so the dot product is negative 33. Well, that is the magnitude of v times the magnitude of w times the cosine of theta. So if I could divide by the magnitudes, I'd be golden. So I need the magnitudes. The magnitude of v is, well, it's a 3, 4, 5 triangle. So I'm going to jump to that because I recognize it. The magnitude of w, oh, I'm pretty sure this is a 5, 12, 13. So I'm going to jump to that too. If I'm wrong, sorry. Math is all the same, just the numbers don't work out. So I'm pretty sure the magnitude of w is 13. So I'm going to take my negative 33 and divide by 5 times 13, which is 65. Notice that now this number is less than 1. That's important because the cosine of theta must be between negative 1 and 1. And this number is. It wasn't before. It's not just the dot product. You have to divide by the magnitudes to put it into the right, well, to be part of this formula appropriately. So that's how I'm not going to get an error, right? If I just try to do cosine equals the dot product, that's not true. It's the magnitudes times the cosine equals the dot product. So my cosine is that, and I inverse cosine this. And now the beauty is these angles are always going to be 0 to 180, and the inverse cosine always gives us 0 to 180. So this one's going to be obtuse, I can tell by the negative, because in our unit circle, these are the negative cosines, these are the positive cosines. And so my angle will be roughly negative 1/2, very, very close to, sorry, that should have been a 60-degree angle. So that puts me very close to 120 degrees. I don't know what it is, but I would inverse cosine this number to find out. And it's probably, I think it's like 121. Like it's really close to 120 because that's really close to a half. Great. Hope that helped. That was quiz B.